Big bursts of star formation in distant dwarf galaxies. Well, we're going to start with a very famous pair of galaxies. This pair of galaxies is called the antennae galaxies. It's a local pair of interacting galaxies. You can see the big long. I wish my. Do you have a?
My left laser sitting on the table there.
Ah, there it is. Because my batteries died, and I tried to get replaced. Ah, there we go. Beautiful. So you can see these big long tidal tails of the antennae galaxies that indicate an interaction between the galaxies. These galaxies are actually smashing together, and if we zoom in on that on the interaction, you can see there's tons and tons of newly formed stars. All of these pink regions in here, all of these bright blue stars indicate star formation, such that we call this a star bursting pair of galaxies. Star bursting in that the star formation rate is so much higher than it is in normal galaxies. And we believe that the star formation rate is induced by the merger of these two galaxies. And so we have studied starbursts, whether they're induced by mergers or other processes, that there seems to need to be a process that induces the star formation rate and pulls it up to big high. And we have studied these starbursts not only in the nearby universe, but also in the distant universe. But in the distant universe, we've only been able to study them for medium and large sized galaxies. However, small galaxies are the dominant by number in the universe. Dwarf galaxies, the meek have already inherited the universe, okay? There are more dwarf galaxies by number than any other type of galaxy in the universe. So when we take a deep image of the universe, you can see that there are a fair number of larger galaxies, but you're dominated by these smaller galaxies. And so this study was looking at the star formation rate, the starburst possibilities in the dwarf galaxies using the new instrument on Hubble, the Wide Field Camera 3, and in particular its infrared capabilities, because by going into the infrared, you can see the starbursts at high redshift and get a good measure of the star formation rate. Well, in this study, here are a few examples of starbursting dwarf galaxies that they found. And they found that these had a very, very high star formation rate, such that these galaxies would double the number of stars in them within 100 million years, or 150 million years. Now, 100 million, 150 million, that's kind of long for you and me. That's really short for a galaxy. Most normal galaxies would take billions of years to double the number of stars in them. So this is a very intense star formation rate. And when they did the calculation, all right, depending upon how they qualified these as these star-bursting dwarfs, they could account from 13 to 34% of the star formation rate at high redshift. High redshift being about 2 to 6 billion years after the Big Bang, or for the cognoscenti in here between redshifts 1 and 2. So looking out into the distant universe, for the first time with Hubble, we're able to actually measure the star formation rate in dwarfs and find that they contribute a significant percentage of the star formation at high redshift. So it's not just the big galaxies that form lots and lots of stars. The dominant galaxies by number, the dwarfs, also are forming a significant percentage of the stars, and this was an unexpected finding. Okay. All right. Our second story tonight. A baby elliptical? Well, let's talk about that. If you look in clusters of galaxies, this is the Perseus cluster of galaxies, and most of the yellow galaxies that you see here are all in the Perseus cluster of galaxies. So therefore, they're about the same distance from us. So you can actually tell size differences. And you can see that in the Perseus cluster of galaxies, you've got these giant ellipticals here in the center. They are the CD galaxies, the central dominant galaxies, the giant ellipticals in there. And they're much larger than, say, the spiral galaxies or others around them. All right? And these are expected to have formed via merging. They're near the center of the cluster. Lots of galaxies, the galaxies that come down to the center, merge together to form these central dominant galaxies in these clusters. And we've looked back in the universe, again, trying to see how these have developed. And we have seen, relatively quiescent. That's interesting. Where did that echo come from? Thomas, we have an echo out here. We got some feedback coming from somewhere.
Fixed it.
Are we getting it? That's better. Okay. So we've gone back out and we've seen them at a reasonable state where they've already formed their basics. All right. But what we were looking for, trying to find, is these galaxies in the process of forming that core, that dense core of stars that's going to start the formation of an elliptical galaxy. Because, all right, so we can see these ellipticals, they've got tons of things, but, when did they form that original ball of stars that started them off? Well, again, we did another deep image with the Hubble Space Telescope, looking for these objects, and not using just images from the Hubble Space Telescope, but also from several other telescopes to verify this. They found this object right here that they say is a candidate for being a core formation of an elliptical galaxy. All right, it is, let me just confirm. All right, so this one is seen as it was 11 billion years ago, which is 3 billion years after the Big Bang. I think that's a redshift of 2.3, if I remember correctly. So looking well out in the universe, this is a galaxy as it was 3 billion years after the Big Bang. And when they met, the size of it is only 6,000 light years across. In contrast, our Milky Way galaxy, which is a fully formed galaxy, is 100,000 light years across. And some of your giant ellipticals are million light years across. So this is very tiny, but it already has as many stars as in our own Milky Way galaxy in that small, compact region. So this is going through a furious starburst. Okay, this is a galaxy at redshift 2.3 undergoing a furious starburst, and the estimates are that it's been undergoing that starburst for about 1 billion years. Now, they couldn't tell that just from the optical light. Hubble's observations couldn't tell us all of that. They actually had to go to the Spitzer Space Telescope and the Herschel Telescope in order to look in the infrared. And what they found was that the infrared light indicated even more star formation than the visible light. The visible light indicated about 1/6 of the star formation that when you went to the infrared, you were able to tell. What the infrared indicates is that the reason we haven't seen these galaxies before is that they are heavily obscured. The formation of the stars spews up a lot of dust. And astronomers, we call this reddening, okay? That there's dust blocking the visible light. All right? And so that they haven't seen these before because there's so much dust in all this rampant star formation being kicked up that it's not easily visible. But this is the first time they were able to see it, and they would expect this galaxy that seen 11 billion years ago, in the intervening 11 billion years, whatever it looks like today, all right, would be a giant elliptical today. So the true question that they have is, now that they found one, how large of a population is there? And that they don't know, okay? Because, hey, you've only got one. How many more of these are there? Are they heavily reddened? We need to go to the infrared to find it. So the answer is, of course, the James Webb Space Telescope. Come on, you guys got to know the answer to everything around here is going to be the James Webb Space Telescope, right? Because that's the next of NASA's great observatories. It, however, is truly going to be the answer because it has the infrared sensitivity, it has the resolution of Hubble, it will be able to find things like this. So effectively, we have found a candidate object for a population to discover with the James Webb Space Telescope. We may be seeing a baby elliptical, and might we be able to see a flock of baby ellipticals with JWST. All right, our final story for tonight I called a space oddity. I was trying to make some pun off of 2001: A Space Odyssey, and I came up with all sorts of things, and I said, all right, we'll just call it a space oddity because it is actually a really strange object out there. Sometimes you find really crazy things. Now, this is something that I've shown you before. All right, you may not remember it, but I've shown you it before. This is the galaxy cluster Abell 68. And ABL 68 is one of those really massive clusters of galaxies that does gravitational lensing. All right, and that comes out of Einstein's theory of general relativity. Mass warps space, and that the mass of the cluster acts like a lens and distorts the images of galaxies behind it. In particular, it distorts the image of this galaxy right here, all right, which looks like that. It doesn't look like it belongs in a cluster of galaxy. It belongs in a 1970s, 80s video game. We call this the Space Invader Galaxy. All right, if there are any young kids in the audience, you probably don't know what we're talking about, but your parents had a lot of fun with this, okay? Way back when. All right, now this is, of course, not the way the galaxy truly looks, because it's gravitationally lensed, and these two yellow dots here are just mirror images of the same yellow dot in the galaxy. The galaxy has been lensed so that it appears twice in the image. You get two images of it that are almost mirror reflections of it, and you end up with this beautiful Space Invader cartoon. All right, this is a cool trick of gravitational lensing. But in ABL 68, there's also another strange oddity in there. This galaxy up here in the corner, and if I blow that up there, it looks like a galaxy that's crying, and all the tears are streaming down. Well, that's not actually gravitational lensing. That's not tears streaming down. That's what we call ram pressure stripping. The galaxy is going through the intra-cluster medium. The gas between the galaxy is actually stripping material out of the galaxy. So we've got two strange things in ABL 68. One due to gravitational lensing, one due to basic physics of ram pressure stripping. Okay, the pressure of the material pulling things out. So, what do we have when we see something brand new like this? Here we have another large cluster of galaxies. It was chosen because it also does gravitational lensing. You can see all these arcs and everything and all these streaky things that say, oh, there's gravitational lensing going on. And right at the core, you see this really strange thing. And your first thought is definitely going to be, oh, of course, that's just some artifact of gravitational lensing. All right, those galaxies in the center are so massive that they're distorting some background blue galaxy. Well, they did some observations and they proved it was not gravitational lensing. And so now you're scratching your head going, okay, if that's not gravitational lensing, what is it? And you look at it in detail and you can see that it's sort of this spiral shape stringy thing with lots of dots of stuff on it wrapped in between two galaxies that look like they're merging together and interacting. And what they figured out is going on here is these blue dots are what they call super star clusters of tens of thousands of stars. Not quite big enough to be globular clusters, but very big star clusters that they believe form in starbursting things. Okay? So let me just check my notes here. Oops, it's this one here. Okay. All right. And what they look at this and they say, okay, well, you've got this string of material, and then you've got these knots forming within it to form these super star clusters. And it's really cool because this is what we call the Jeans instability in astronomy, the self-gravitation of the material that collapses to form these things, these sort of pearls on the string. And it's similar to how you form water droplets out of the laminar flow out of your kitchen sink. So if you've got your kitchen faucet and the water's coming out smoothly, eventually it will form little droplets. Now, it's not an exact analogy in my opinion because this involves a little bit of turbulence and Reynolds number, which is not necessarily involved in the Jeans thing. You've also got the surface tension of the water, which plays a significant role here, which doesn't happen in the gravitational one, but it is a good enough analogy in terms of how you form these things along these strings. And so you can figure out, okay, great, you've got that. You've got the analogy. You can see that things from your kitchen sink, the physics of your kitchen sink can actually apply on galactic scales. That's really cool. But we don't really actually have a reason for why that material is there in the first place. That you've got this long string, 100,000 light years in length of material that then somehow subfragments to form these super star clusters. And in the press release, they offered up 3 different possible explanations. none of which truly convinced me. I didn't like any of them. One of them sounds best, but it didn't sound like we really knew what was going on. All right, and I was giving a teacher training workshop this afternoon, and one of the teachers asked me, well, what happens when you see things that you don't know what they are? I mean, is JWST going to find things that we're just going to not know? And I said, you know what happens then? Then you're really excited, because it's a great day for an astronomer when he realizes, I don't know what I'm looking at. This is something brand new. This is a new phenomenon. This is something weird we haven't seen before in these things. And so it gives us something new in the universe to uncover. This is something new. We can tell what's going on there, that you've got these superstar clusters and these two galaxies are merging, but we haven't seen this before. So we're going to have to work hard to try and explain it and understand it. And that's what really should be exciting. Ignorance is not, it really is bliss, because it shows you that there's something new to discover in the universe. Okay, so that is our news from the universe, and now it's time to move on to our featured speaker. Our speaker tonight, hold on, I guess I have to. Our speaker tonight is Marshall Perrin of the Space Telescope Science Institute. Marshall started his career getting his undergraduate degree at Harvard, and then, like me, he went to Berkeley and got his graduate degree. He worked at UCLA on the project he's going to talk to you tonight, before coming here to Space Telescope 4 years ago. And here at Space Telescope, he works on JWST instrumentation. Ladies and gentlemen, Dr. Marshall Perrin.
Thank you all. Can you hear me in the back? Great, good. Well, it is a pleasure to be here tonight, and a pleasure to talk about what we've been doing lately to take pictures of planets around other stars with an instrument we call the Gemini Planet Imager. And Frank earlier said, he made a comment that there's astronomers that are observers, and there's astronomers that are theorists, and there are those that write big computer simulations. So there's also those of us who build hardware, who build the machines that are used by the community. And we do this on the ground to build new instruments for big telescopes. This is the Gemini South Telescope in the Andes in Chile, and also working to build new instruments and hardware for future space telescopes. And so I'll tell you that. And so this is in part a story about what we know about planets around other stars and what we're learning. And it's in part a story about the process through which we build these machines to take pictures of things that have never been done before. And that's a process that involves really a whole lot of people. This is just a list here, and I won't go through the names, of course, but of the collaborators that have gone together into building this instrument, the Gemini Planet Imager. It's a project that came out of the University of California, but has collaborators from Canada to Chile to New York, of course, to here, and everyone working from grad students to postdocs to senior scientists, and as well as engineers and computer programmers that all go together to make a new instrument for one of the largest telescopes on the ground. So what I'll talk about in the next hour or so, start off with the motivation. Why do we want to take pictures of planets around other stars? What are we going to learn from doing this? And how does that actually motivate us to do what turns out to be a tremendously difficult challenge? Secondly, how do we meet that challenge by building a new instrument? This instrument, the Gemini Planet Imager, as a camera. Think of a car-sized camera on the back of a house-sized telescope. And so once we've developed and tested that, taken it to the telescope, which we did last November after 10 years of work to bring it and get the first images with this new camera. And I'll say a bit about what we've learned so far and what we hope to learn in coming years with this instrument, and then looking beyond to future space missions that'll tell us even more. So to begin with, some context about the landscape of exoplanets. And I'm sure many of you have heard talks about exoplanets here and at other places in recent years, and that's because it's become one of the most exciting areas of astrophysics in recent years. There's just been this amazing explosion in discoveries of exoplanets. So what I'm showing here is a plot. This is a histogram of the number of planets that we know about around other stars versus the year of discovery. And this really starts in the mid-90s. With some first discoveries ramping up very gradually. And in these first years, it was very controversial whether these really were planets or not. And as the field started to take off, it became really clear, yes, we do have the techniques to find planets or other stars. And I'll say a bit about those in the next slides. And then really in recent years, it's ramped up with dramatic new discoveries with these different methods of finding planets. In green, the radial velocity method. in blue, the transit method. You may have heard about the Kepler spacecraft. And these really big jumps here are where the Kepler spacecraft has been successful in finding hundreds and now almost 1,000 planets that we know about in nearby stars. And then these little tiny wedges on top of the histogram from a technique called microlensing, and then what I'll be speaking the most about, actually imaging and taking pictures of these planets from other stars. So what are these four methods that we use? So radial velocities is an indirect method. We can't see the planets yet, but you can see the stars, right? The stars are bright, they're self-luminous, and in their atmospheres, you can measure the Doppler shift of the star, the red shift and blue shift as the star moves towards or away from you. And so think about this. You have a planet that's going around the star. Well, the star is wobbling a little bit in that. And the analogy I like to use, I think about picking up my 3-year-old and spinning him around, right? And I'm actually moving in a little circle in the middle as he's spinning around me. And so the star is actually moving a little bit as the planet goes around it. And by measuring that motion, we can infer the presence of these unseen planets. The other way you can detect planets indirectly, you're not seeing them, the light of the planet itself, but you can see if the planet happens to be lined up, that as it orbits the star, it eclipses. It comes between you and the star, and it will block a little bit of the starlight. Well, a planet is, of course, much smaller than the star. This Earth is about 1% the size of the sun, so this is not a full eclipse. It's a 1% eclipse. But if you measure that, and it happens every 3 months, you say, oh, there's a planet that goes around that star every 3 months, and you've learned the size of the planet and something about its orbit. Frank actually just gave a great introduction to this one, gravitational microlensing. We were just seeing these wonderful arcs and distorted images made by galaxies in the distant universes, but the same thing can happen in the Milky Way galaxy. Think about our own spiral galaxy, and all the stars are moving around the center of the galaxy very slowly, but every so often 2 stars will line up, right? And the star in between will act gravitationally to magnify the light of the star that's further away. Now, if the star is in the middle, has a planet around it, both the star and the planet out here, imagine you have a magnifying glass with a little bump on the side of it, right? You can measure, oh, there's a distortion there. This is not a simple magnifying glass. There's a planet orbiting this star. And so by watching this, as stars move, you see them brighten and dim. You can infer the presence of these planets. And of course, what I'll be talking the most about is just simply imaging the planet. This is simply, right? That's the joke. This turns out to be extraordinarily difficult, probably the hardest of these 4 methods. Here, imagine there's a star here that we've blocked out, and I'll say how we go about doing that. And in this case, we can see 4 planets that are orbiting this star. And these turn out to be 4 planets about 10 times the size of Jupiter that are orbiting even further than Saturn and Uranus and Neptune are from our own sun. So this is a very big, very massive planetary system. And so all these methods have been developed over the last 10, 20 years, and they've really been taking off as we find all these planets. So this is a plot showing in a different way the same set of planets that we know about. But here I'm graphing the mass of the planet versus the distance from the star. So these are the big, massive planets. These are small planets down here. And I've put our solar system's planets on for context, right? Here's Jupiter up here, here's the Earth. And so you can sort of see what types of planets we've been finding, right? And the same color code for the different methods. And it's actually very interesting to see that there's different clumps of types of planets, that there are these big Jupiter-type planets in this area. We find some that are very, very close to the stars, which is something no one predicted before this field began. And of course, the most planets we're finding now are these lower mass planets found in this regime down here, that are planets with similar masses as between sort of Earth mass and Neptune mass in this range, but they're actually closer to their stars than even Mercury is to the sun. I should say Mercury and Mars are shown here, though they're off the bottom of the graph for the vertical axis. And so these 4 methods have just been gradually filling in this part of parameter space. We don't yet have the ability to really find planets that are just like the Earth. We're just barely beginning to do that. And as time goes on, we'll start filling in more of this graph. Now, the reason it's worth having all these different methods is they all have different strengths and weaknesses. The radial velocity method is best at finding these massive planets, the ones that make the star wobble a lot. But you have to watch the whole orbit around at least once, hopefully twice or more, to see the elements, the chemicals that are there, will absorb the light differently when it passes in front of the star. So you can start to get some composition information via the transit method. Microlensing, of course, similarly, you have to get lucky in this case, and that's you have to have, as this galaxy orbits, one star passes right in between you and the next star. And you have to be watching it when that happens to see this temporary lensing event that might last for a few months, perhaps, or even a few weeks or less, as the brightness ramps up and then goes down as the two stars move past each other in their orbit around the galaxy. Now, you may think stars don't move that fast, but it turns out to have a good probability of this. You're looking towards the galactic center where there's tons of stars. If you look far away from the galactic center, there's just not enough stars. You're never going to have these chance alignments. The big problem with microlensing is it's a one-shot deal, right? The stars keep moving, it goes past it. You're never going to see that lensing event again. You get one chance to find there's a planet there on that star. You're never going to learn something back again. You can't go back and characterize it and study the planet in more detail. So it gives you good planets orbiting within half the distance of the Earth to the Sun. You know, that's this clump down here, 10 times closer to its star than Mercury is to our Sun. Right? There's nothing in our solar system like that. This is a scorching hot Jupiter. It's about 2,000 degrees there. You know, it's just a very alien planet. And we have some of these planets are on very elliptical orbits, not the circles of our own solar system, but planets that go 10 times closer and 10 times further from the star on these very, very oval elliptical orbits. There's this class of planets that people call super-Earths or sub-Neptunes. You know, we don't have any planets in the solar system that are 5 times bigger than the Earth. You jump right from the Earth to Neptune and Uranus that are 16 and 18 times more massive than the Earth. So what's a planet like that's 5 times more massive than the Earth? Is it rocky? Is it like a mini Neptune? Is it a big Earth? We don't know yet. And there's still this gap in planets at wide separations, the beyond 10-year orbital periods. And that's really limited by these methods that require watching full orbits. And so this is the first motivation for why we want to take pictures of exoplanets, is because this lets us explore these outer regions of solar systems, detect the planets that are there, but more than just detect them, we can characterize them, we can study their compositions and their properties and understand how common are these planets like Jupiter and Saturn, how do their atmospheres work, how do they evolve with time. And so really you want to ideally combine multiple methods. If you can get each one measures something different. Radial velocity measures masses, transits measures radii, only transits and imaging can measure the spectra and tell you about compositions. And so as you put together all these methods, we gain a bigger picture of what's going on in these solar systems. And so if we take, I said we can't measure with confidence how many stars have Earths, but there's nothing stopping us from extrapolating, right? You take the Kepler measurements at slightly smaller separations, you take how they depend with radius from the star, and you can make an educated guess. And it looks like something like 10 to 20% of stars probably have Earth-sized planets, within 1 or 2 times the size of the Earth, orbiting at roughly the distance of what we call the habitable zone, the zone where the planet's temperature is about that right to have liquid water, to have clouds, to have atmospheric circulation. Now these numbers are tremendously debated right now. Some people say it's 5%, some people say it's 20%, and what exactly does the habitable zone mean? And there's a lot of activity and excitement about trying to pin these things down. This was something the Kepler spacecraft was really designed to try to nail this question down. They haven't quite got there yet. As you may know, they had some mechanical issues in the spacecraft. They've managed to salvage it and are going on to do more science. And so we're hopefully going to have better knowledge in a few more years as the statistics keep getting better. But we're not quite at the point where we can detect a true Earth twin in most cases. And they're certainly beyond our capability to characterize and study. And that's really the second key motivation for why we want to image exoplanets, is to get a pathway to understanding eventually the compositions of Earth-like worlds, that we can measure their atmospheres, we can understand perhaps how planets form, we can understand how planetary systems evolve through time. The Earth started out with a very different atmosphere than it has today, a carbon-rich atmosphere, carbon and nitrogen-rich, and over time the planet oxygenated due to the activity of bacteria in the sea. And the oxygen atmosphere of the Earth is a relatively recent phenomenon, and so that's something we could actually detect on a different world. And that might be a sign of life. You could look for signs of the chemistry of atmosphere. You might have methane and oxygen and what we call biomarkers, biosignatures, that would show up from afar, and I like to think this is sort of, we've all probably seen Star Trek, and they're going out to, seek out strange new worlds and signs of life. We'd all love to do it in a spaceship. We don't have that spaceship yet, but we do have big telescopes. Right? So this is what we're trying to do. Now, I said that these Earth-like planets are mostly beyond the reach for our detection. And one example for that here is this is a discovery, a paper that came out in April, a planet called Kepler 186f. And this is the most Earth-like planet known so far. And this is a copy of just the start of the paper in Science magazine. And so it's an Earth-sized planet in the habitable zone of a cool star. And so you see this beautiful artist's interpretation of what this planet might look like, and it's kind of golden color, and it's got clouds, and there's some weather, and it's a bit bigger than the Earth. And if you read through the paper, you say, well, of course, this is what an artist says. What do we actually know? Well, this is what we actually know. We have this measurement of the transit. This is the detection of the planet, where you see the star's brightness over time, and then it gets a bit dimmer, and then it comes back up. And this repeated time after time is the signal that there's this planet that's orbiting in front of the star. And based on this measurements and a lot of careful detective work, you can figure out that it's about 1.1 times the radius of the Earth. The mass is very unconstrained, but if you take a range of things it could be made of, it could be solid rock, it could be solid water, it could be mixes in between. It's probably about 1.5 times the mass of the Earth, but with a huge uncertainty on that. And we know that it takes about 130 days to go around its star. The star is about half the size of the sun, so it's cooler. So this golden color is this is a dimmer, redder sun than the star. And so all the details of atmosphere and chemistry and liquid water there, it's at the right temperature to have liquid water. And it's actually, under some educated guesses, the temperature says it should be a bit colder than the Earth. So they've drawn in these big ice caps on both sides, and only this part has liquid water, and up here it's all very frozen. And so maybe that's the case. And we would love to be able to fill in some details in this artist's rendition and actually say, this is what's going on here. And, I sort of played this, a bit for laughs, that this is all we know. There's a lot that goes into measuring this and trying to figure out that and ruling out other things that could cause this transit signal. It's a tremendous amount of work to get to even this much data on a planet that's very distant. And the challenge really comes down to the fact that I like this picture because it shows the real problem, which is the glare of the stars. Right? The planets are not self-luminous. They're not glowing. The star, on the other hand, is fantastically bright. And so if you look around a planet that's near a star, these asteroid belts, comets, anything you want to see in one of these nearby solar systems, right? You're doing it against the challenge of the glare of the central star. And you can see that in our own solar system here. This is a picture from a solar eclipse seen in Mongolia a few years ago. And it's a nice shot because you see not just the sun here eclipsed by the moon, but these two faint dots in the sky near, scattered light around the star. Right? You've probably all seen many, many images that have this sort of cross-shaped pattern. Right? That's actually an artifact of the telescope. The telescope's secondary mirror is held up on a cross-shaped pair of supports. And so you get the scattered light from that. And you get this more sort of glare, halo coming off, even with the telescope in space, even with Hubble. And in fact, if you stretch the brightness of your image hard enough, you're trying to see things billions of times or millions of times fainter than the star, you find out that the entire field is full of starlight. Everywhere you look, even with a Hubble class, gorgeous telescope, there's just excess glare and light when you're trying to see things that are this faint. And so this is what we call contrast. Right? The contrast is the ratio between the bright thing in the middle of the field of view and think about is the name of the game here is to take one of the biggest telescopes either on the ground or in space, pointed at naked eye bright stars that you can easily see and not see the star. Right? Block out the star and see the planet that's there. Another way of looking at this quantitatively, right, is just to plot the contrast, that ratio again, versus the separation from the star. And we'll see, so here's these luminous young Jupiters, the glowing red-hot Jupiters, and these dots show planets we know about already. And these ones up here are brown dwarfs, are intermediate objects between planets and stars. And down here we have the orbits of planets in our own solar system. And these gray curves actually show the variation in the brightness. You can imagine as the planet orbits around the star, it's going to show phases. Just like Mercury or Venus show phases as they go around the sun. And so its apparent brightness of the planet changes with time. This is another complicating factor. But so down here, we're at this billion times fainter than the star region. But in terms of separation, if you're looking at planets that are at stars 30 light years away, 10 parsecs, the separation is between a tenth of an arc second and an arc second. And if you're familiar with the kinds of imaging we do with instruments like Hubble, that's actually not very hard. The challenge is not getting close to stars. The challenge is entirely in seeing how faint these things are. So how do we do this? How do you take a picture of something that's 1,000,000 times fainter or 10 million times fainter than the star it's right next to? Well, the first thing you want to do is start with some nice crisp images at many times a second to basically cancel out the distortion and give you crisp images from the ground. And this is a technology that's been developed over the last 20 years. You'll often see, in some cases, people use lasers to measure the distortion in the atmosphere. In this case, we know we're always looking at a nice bright star in the middle of our field of view, because that's what's got the planets. So we can measure how sharp the image of the star is and say any blurring and distortion in that must be because of the atmosphere. So let's put on the opposite of that distortion on the mirror, and it cancels out. And so you imagine you take this bumpy, unfocused light and bounce it off a bumpy mirror, and it just cancels out, and you get very sharply focused images on the camera. Once you've got your nice sharp image, you then need to block out the starlight. And here we use a device called the coronagraph. And this is something that was invented by Bernard Liot, a French astronomer, almost 100 years ago, who was studying the corona of the sun, all that beautiful outer atmosphere of the sun that we were just looking at during the eclipse photo. Well, he wanted to study that without the pain of having to wait for an eclipse every few years. So he said, can't I make a pretty mature field? Of course, I was just earlier today on an all-day telecon with people at NASA Ames talking about designs and tests of the next most advanced coronagraphs for a future spacecraft. And I'll say more about that later. And so you take and you block out most of the mass of the sun, and there are these spiral arms and all sorts of complex structure in the dust around this star. And the only way to see it is by subtracting off all the stuff that gets through your instrument. And so this is really a matter of having multiple tools in your toolbox. You block as much light as you can by getting rid of the scattered, the glare of the atmosphere, the distortions of the atmosphere. You get rid of that. Well, then you have a coronagraph to block all the scattered light that's left over from that. And then you do software image enhancement to block as much as you can from that. And so you put all these tools together, and you start to be able to dig down to these factors of 1,000,000 times fainter that we want to be able to do. So with Hubble, this really began, as I said, in these studies of circumstellar disks. And so you can see that this is just a handful of these systems where we're looking at young nearby stars, and you can see the complexity of the structure around them that you have. This is a ring. Think about our solar really began in 2008 with two discoveries in short succession. One is this object Fomalhaut b. And so here's a ring, one of these rings around. This is one of the brightest stars in the sky, Fomalhaut. And my colleague and friend Paul Callis noticed there's a little dot just inside the ring, and it's barely there. It's about 1 billion times fainter than the light from the star, but you can see it. And now, after many years of study, we're still not quite sure what this is. It seems like it might not be a planet. It might be a cloud of dust and gas. It might be two asteroids that have just collided and let out a whole bunch of debris. So there's certainly something there. This one is still one of those mysteries we heard about. We don't quite understand what's going on with this one. It turns out also, we thought it was going to orbit right inside the ring. It's actually orbiting crossing the ring. So something's going on. It's still a puzzle. And then this other one, HR 8799, is the address code of the star. Or again, you start out with, even with the coronagraph from this telescope to block the starlight, leftover splodges of light, the light that gets through the system and just the glare. But with very careful post-processing, you can start to see the planets that are orbiting the star. And I should say, this is a Hubble image that I'm showing because I'm here. This was not the discovery image of that planet. That was done actually from the ground by my colleague Christian Marois. And so this is an image by Christian with the Gemini telescope with the previous generation of instruments, where you can see these four. It turns out first there were three that were known, then this more innermost planet was found, planets B, C, D, and E. The star gets called A, so planets always start with B. And so we now know these are 4 planets orbiting around the star. It's the only multi-planet system that's been imaged yet. Beta Pictoris, another very famous star, one of the brightest ones in the sky. It's long been known to have a big edge-on circumstellar disk. This was actually the first circumstellar disk to be seen and imaged 30 years ago. In fact, next week there's a conference in France, 30 years of Beta Pictoris, honoring this discovery, and that launched the whole field of studying circumstellar disks. And it's been discovered recently, well, 5 years ago now, by Anne-Marie Lagrange, that there is a planet that can be detected inside this disk, orbiting in the same plane as this edge-on ring around the star. And I'll come back and show some more data of this one later. And in recent years, using instruments on the ground, we've been able to find a handful of these. But this really is a near complete set. Remember going back to the charts I was showing at the start, hundreds of planets found by radial velocity, hundreds of planets found by imaging, or sorry, by other methods. And so we just have a tiny, tiny number seen with imaging. So that's why we need these new institution team. And so we had in 2006 an official project start, and then years of design and development and simulations and putting together, working with engineers, how the machines might work, how the optical design could work, and then start in 2009 or so, really putting the pieces together, the metal and the glass and the electronics that goes into the instrument. So what are these pieces? What's inside the box, right? There's a number of different subsystems that make up an exoplanet imager. So first is the adaptive optics system. And this is a view looking down on it. It's actually about life size as it's projected on the screen here. And the light bounces through in a complicated path and bounces off the deformable mirrors that run, and there's two of them in there to correct the atmospheric turbulence. And it's like your stereo speaker at home. Some do the low frequencies, some do the high frequencies, and the two of them work together. And they run, the high order deformable mirror is 1,800 actuators. So you imagine the big 8-meter telescope, break it up into 20-centimeter chunks, and each of those has a little actuator corresponding to it to keep it in focus, running at 1,000 times a second. We also use super polished optics, 1 nanometer surface quality smooth, some of the finest optics you can buy, because if you don't have the scattered light and the glare in the first place, it makes your life easier. The light is actually, I mentioned these deformable mirrors. This is what it looks like. It's a focus to a camera called an integral field spectrograph. The goal here is not just imaging, but spectra for every single pixel. And so you can imagine each pixel in the image you break up into its own little rainbow spectrum, so you can measure multiple wavelengths of light. We're used to digital camera images that have red, green, blue, right? This takes maybe 20 colors per image. And that gives us enough spectral resolution. It's not very high compared to what many people do for spectroscopy, but it's enough to see some of the absorption features and properties of the atmospheres of these planets. And this is the piece that I was most directly involved in building and fabricating when I was at the University of California, Los Angeles, and I'm still deeply involved in now, leading the group that does the software for this instrument. The raw data is a pretty complicated beast to look at. This is a shot of a planet where you can see the starlight here. There's still a little bit of residual light. There are these 4 reference spots. These are intentional little grid of spots we use to calibrate the position and brightness of planets. But if you zoom in on the center of this and see what we're actually looking at here is about 36,000 little spectra. And while this is hard to interpret and wrap your head around what's going on, but we have a data pipeline, computer imagery software that reconstructs from this and puts together a data cube, what we call a multispectral image. So here we're looking at the wavelength of light changing between 1.5 and 1.8 microns. And you can see this scaling pattern is the way the starlight changes the wavelength due to something called the diffraction of light. And so we can use just over a year ago. So here's the instrument pulling up to Gemini Observatory at the summit. And of course you have to then unpack and take out the warehouse full of boxes and reassemble finally the instrument there. And again, a whole period of testing to make sure that you've successfully reassembled and reestablished it there. And Gemini has a big crane to pick up and hold the instrument there and move it around the same way it'll be swung around in the telescope. And when you're on this crane, it's getting the same data and power and telecom. So the instrument thinks it's on the telescope, right? You can do very extensive testing. And then in October, right, taking it up and bringing it up and craning it up. And so finally, in October, we finally had the instrument, after 10 years of work, assembled right in there. And that's our image with the Gemini Planet Imager. And of course, this planet has been seen before, and I can show you an image here with an instrument called NICI, the Near Infrared Chronographic Imager. This is Gemini's previous generation instrument. So it's the same telescope, but it's about a 6 or 7 year older camera. And you can see there's a little faint dot there. It's maybe a little harder to see than this one, but you can detect it, right? However, the thing that I didn't tell you here is this image we got in 60 seconds. That one took over an hour. So we were pretty happy about this. It is dramatically more significant, more sensitive, much more capable at seeing these faint planets. When you put together not a minute's worth, barely a snapshot, but a whole hour's worth, you get rid of all engineering. We've also been taking time to do some observations and science measurements. How better to test a new instrument than by using it to do science and do discovery? So just some quick highlights from that. Planet Beta Pictoris b, right? We can measure its position very carefully with our instrument. And now this is a plot showing the x and y position of the planet relative to the star over time, measured with older instruments here. These are the discovery images. They were able to go back and find some archival data where it had been missed and dig out a very early data point. And we measured its position here in 2013. And you can actually start to see that the planet's orbit, you can get planets orbiting back and forth from the star, right? It goes out further on one side, then it starts to swing back the other way. We were able to see it swinging back in the other way in a very circular, very edge-on orbit, much like that of Jupiter in our own solar system. The part that's interesting, of course, is because it's an edge-on disk, and this is where the orbit was going to look like it goes in front of the star. And we were predicting, based on this data, there's about a 4% probability that this planet will transit, which would be amazing. If we had a transiting and directly imaged planet, we would learn so much. And there's actually previously been some data. There was a paper back in the early 80s about something weird going on with the star, and it seemed to dim for a little while. And it all holds together as a story that it could actually be, but it's still a low probability. So I wouldn't expect to be going on in the atmospheres of brown dwarfs and lower mass planets, where there's all this complex chemistry and cloud formation. We know this on Jupiter, right? Jupiter has all these bands and different types of atmosphere in different regions. And so what we expected was that we have lots of methane gas up high in these low mass, relatively cool objects. And we're not seeing that. We're seeing instead that it's mostly dominated by carbon monoxide. And what that's telling us, a very recent paper out by Kevin Zonley and Mark Marley, that it's telling us about the chemistry in the atmosphere of these planets. There has to be this carbon monoxide is getting dredged up by vertical circulation to the tops of the clouds in the young planets that doesn't happen in the more mature planets. It's telling us there's things that are different. Even though these planets are 10 or 100 million years old, their atmosphere is still showing signs of the formation process is still more active, churning than more mature planets. And so that's something we're still going to be. Again, this is one of these recent puzzles where I'm sure as we get to more planets that have been imaged, we'll have a lot more to say about what's going on in their atmospheric chemistry. That's something we really intend to push on a lot. We can also use the Gemini Planet Imager to look not at exoplanets, but their instrument called SPHERE. After 10 years, both instruments, I should have said, got to the telescope about 3 years late. We hoped to be there earlier, but we just got there now. But they both got there at basically the same exact time. They're as good as we are. They're as polished as we are. They're just a couple months behind us, but their instrument has, here's a picture of the same ring around that same star. Here's a stellar companion at 1/4 of an arc second, attached to their 8-meter telescope. They're very comparable systems, which is actually good. If you think about the big stories in astronomy, whether it's radial velocity exoplanets or the expanding universe, having two teams is good. You can cross-check each other's, you can validate each other's results. Occasionally you keep somebody else on their toes by doing something better than the other team did. You can hire their students to come be your postdocs. We'll keep telling ourselves, right, competition is good. On the other hand, we're glad that we're the ones who are right now a couple months ahead of them. So we're going to try to keep it that way. But it's a fantastic team. Don't get me wrong, we're all personal friends with a lot of these people. We've been, talking to each other and learning a lot from each other. It's actually very interesting. There's some technologies that people on my team invented that are working better on their instrument than they're working on ours. So we're going to learn something from that. It's a good partnership. And I should say that the Japanese national facility Subaru also have some good instruments that they're building in this area. Other facilities as well. It's really a very active area on the ground. This will keep us busy for at least the next 5 or 10 years, exploring and finding many dozens of Jupiters and characterizing and understanding what their properties are. The last few things I want to say, a few more slides about, is where do we go next, right? We have this beautiful cartoon of a terrestrial exoplanet that we would like to learn more about. Well, there's the James Webb Space Telescope. Frank said it's got all the answers. In this case, it's some of the answers. It's not all of them, it turns out. We're going to have very high sensitivity. It's going to be able to see incredibly faint little planets, but it's not really optimized for all this really excellent coronagraphic suppression of stars. It does have several coronagraphs on them, but technology takes a while to get into space, right? So all the technology for JWST was go. Another government agency, let's just say, has given NASA some spare Hubble-class telescopes in a warehouse in New York. They don't need them anymore. They have three. Three that they're not using, right? Let alone the ones they've already got up there, not pointing up. So we've got a couple of these, right? What do you want to do with them? Well, what we're going to do is we're going to put a wide field instrument on it. Hubble-class imaging, 100 times the field of view, 1/3 of a gigapixel in space. Just tile the sky with gorgeous Hubble. Up here, we could see something that's a few times bigger than the Earth. And so I think this is going to be, I mentioned before, there's this weird class of planets that's a bit bigger than the Earth, a bit smaller than Neptune. There's nothing like it in our solar system. We can take pictures of them with this instrument, and we'll be able to characterize what those look like, and look at their atmosphere, look at the spectra, and figure out what their compositions are and how they fit into the broader picture of planetary systems. But we're still not at Earth's. What does it take to do an Earth, right? That's what everybody wants to know. Well, it probably takes something like this. This is a recent NASA design study. I'm part of the group that's been working on with many other people. Something like a 10 to 16 meter space telescope. And there have been a number of different studies. ATLAS, the Advanced Technology Large Aperture Space Telescope. HDST, the High Definition Space Telescope. Right? And what we want to do here is the advance that's going from Hubble to JWST, do it again. Right? Which is crazy. Let's take a telescope bigger than anything that exists on the ground right now and launch it into space. But it was crazy to think about putting a 2.5 meter telescope in space. It was crazy to think about having astronauts go up there and fix it. Right? It was crazy to think about JWST with this giant unfolding sun shield that I just showed you a picture of. Right? So you can do crazy things when you are patient. That's the takeaway in instrumentation is, we're getting to the point where we're going to launch JWST in a few years after 20 years of work. Building an instrument for a ground-based system now takes 10 years. Building one of these is going to be one thing, and a year inventing something else, and 6 months trying the next thing and putting all the pieces together. And by doing so, we hope to go from Jupiters now in infrared light as they glow to optical scattered light imaging with W first of Jupiter twins and super Earths. To maybe 20 years from now, be able to say something about what the properties are like of terrestrial planets and what their atmospheres are. So that's what I had to say, and thank you for being here, and hopefully take some questions. Yes, sir.
That was stunning.
It is the work of many people.
If you hadn't shown us the pictures of the hardware, we would have thought you made it all up.
I feel very lucky to come in at the end of 20 years of work on JWST and be part of the team for the last 4 years. Heidi Hamill, who's someone that I look up to as a mentor, has talked about being here, being in the right place at the right time to work on Hubble, right, and being there when Hubble was launched. And that's really lucky to be able to be part of that, even if they just hand it on to the next generation. And we're also very lucky to have the support of NASA and the European community, the Canadian community, and to be able to do this. Great.
Let me just comment that we're live streaming this over YouTube, and several people on YouTube are making similar comments like that. And they're just trying to wrap their brains around these integrated field units in terms of getting spectra at every pixel and everything. Yeah, it's really cool technology that's really opening up the field.
Well, now I have a question.
Yes.
Okay. There are short periods in this time. Life on Earth is for a short period of the
Yes.
life extension of Earth.
Well, life on Earth has been around for almost the entirety of the age of the Earth, gradually changing the atmosphere. People look at this and say, what would the Earth look like at 1 billion years, at 2 billion years, at 4 billion years? How can we recognize that? But that absolutely is going to be a huge challenge. But what we get at the end of the day, for many years of effort and probably a Hubble-sized mountain of money, is going to be a spectrum that tells us, it probably will raise more questions than it answers in terms of what's truly going on there. And absolutely, it will be a challenge to interpret and understand. But we'll have to do it in context of what we know about biochemistry. There's a whole field of astrobiology devoted to trying to understand what are the best signs to look for, what are the best lines. And people have recently been saying, well, you need to do this in space in the infrared, which makes it even harder. It drives you to a bigger telescope. So there's a lot to do. Are there other questions? Yes.
Yes, you kept mentioning the circumstellar disk.
Yes.
Is that different from a protoplanetary disk?
So a circumstellar disk is a broader category. There's two types of disks. There's protoplanetary disks, when stars are young, and you're colliding together and building, you're rolling up the snowballs to build larger and larger objects, to build planets. There's also something called debris disks, which is what the solar system has more now. We don't have collisions that build up larger things. You actually have collisions that grind down and are destructive. You think about it, if you have a rock and you smash it with another rock, you generally don't get a bigger rock. You get fragments, right? And that's the regime the solar system is in right now. So you have the young planet-building disks, and then later you go to the debris stage, where there's much less material for various reasons. The collisions tend to be higher velocity, and it's more like the asteroid belt of our own solar system. So those both get classed as circumstellar disks.
Okay, other questions? We're getting late. It's a little past 9:30. I usually cut it off at 9:30, but I'll allow one more question down here.
I've been following Magellan AO.
Yes,
which is
Magellan
down
AO.
there too, and that also uses an atmospheric correction process that has resolution better than Hubble.
The Magellan AO folks are great friends of ours. In fact, there's